All right, welcome everyone. So this is going to be a interesting lecture. So we are going to learn about ROP. Probably you guys are hearing this for the first time. ROP stands for Return Oriented Programming. Return Oriented Programming. We have seen a lot of other uh, programming types: pair programming, object-oriented programming, structured programming, and so there's quite a bit. So now we discuss something called return-oriented programming. So this is something special in cyber security or like the worlds of exploit development, the return-oriented programming. So we'll try to understand what is this concept and basically how we are going to work with this. So this is probably to understand that. All right. So let us start. Right. So to start with this lesson, you have to understand a bit of here and there about exploit development. So we have talked many different types of exploit development. So we talked about basic exploits and then stack-based overflows or the buffer overflows, then stack overflows, heap overflows, and there are the different techniques of doing other exploitations, remote exploitation, Windows exploitations, and also format string exploitations. So there's a quite list that we have learned. And all these different methods would have their own goods and bads. I mean, like pros and cons. There are plenty of them are available, uh, and most of them provides us opportunities to do different types of hacking activities or exploitations. So now, because you have learned buffer flows and other techniques, so now we'll see like, is this possible all the time? Can we do these overflows all the time? And anybody do these things? But of course, the reality is much different. Some of these exploits are not possible these days because of different safe mechanisms that we use, right? So what happens is it's called as a cat and mouse game, right? So cat tries to find a vulnerability of the mouse and then try to find out a way to kill it, right? So and then cat's mouse finds out the mechanisms to get protected. So this is cat and mouse game. So always the bad person, I don't know who is bad at cat and mouse, but bad person tries out the vulnerability and the good guys, security engineers, come up with another techniques to safeguard it. So this is being happening a lot. So especially in terms of most of the attacks it happens in the stack, right? So it's important to understand that most of the things happen in the stack. So there are a lot of techniques used to protect the stack, right? So it's the stack, and most of the techniques are there to protect the stack, and some of these things you have learned, right? So if I take few concepts, initially, of course, we can get stack canaries, right? So you have seen this. We have talked about this earlier as well. So this is the stack guard technique. So basically what happens is when you get the stack, when you fill your information, so you're going to keep a canary in between, a memory location in between before the arguments. So once you fill this in, so what we normal, so this will be injected into the code, this canary value. So canary is a bird actually. So the whole idea came in case where the miners, right? I think in US or somewhere, the miners you go down in the earth and then you build up these things and you go down into them, the mines, and then at one time you find that there are a lot of very poisonous gas created in the mines, and then suddenly they die because they don't have mechanisms to measure it like these days they don't have those devices, uh, these sensors to measure the air quality. So what they do is, this canary is a nice bird, probably have seen them somewhere, right? So let me bring a canary bird. a picture of it, so you remember what is this, right? So canary bird. So these birds are really sensitive, and people really didn't really worried about you know, these birds dying in the mines. Uh, so this is a canary, right? So then they brought canaries, and then when the time where there are gases, these are more sensitive birds, and these birds die. So then the miners knew, okay, there is some problem. So then they try to safeguard their life. So this is something very similar. So this is kind of a monitoring tool. So this, because of the stack canaries, it will indicate the processor that the processors that somebody is trying to overflow this, and then that will stop it. So the stack canaries are a common techniques used, and it's called stack. So this is in default there in some GCC levels compilers, and this is also called stack smashing protection. So we talk about stack smashing, and on default by after GCC 4.1. So once you get your GCC, I think you can get the version GCC. Yes. Yeah, so GCC version, so you can get the GCC version. This will work. Yeah, so this is 4.2.1. Yeah, so this obviously is having stack canaries in it, right? So the old versions might not have it, but this version is having it. So this will give some protection, right? But remember, the hackers, like if you have the ability to stop the other compilation, you can use this particular tag and then a flag and can disable. So once you compile something, you guys can compile in this GCC minus F no. So we have this. So we have to use stack. Is it that there? Yeah, stack protector. Yes, stack protector. You can use this and compile, and then it will basically removes this stack canary. So then you can do the exploitations. But remember, if original file is there with compile in this way, it doesn't, they don't not use this one, so you'll not be able to hack it, or you'll not be able to overflow it, right? And then you have the other mechanisms, right? So there are several other mechanisms which you can use. So there's another one called DEP, or data execution prevention. So it doesn't allow to execute code, but not the data. And data areas marked as non-executable. So this is called NX. So it's a hardware enforced one. So this is normally called as NX, right? So it's called as NX. We talk about this a bit detail. So in next, you can load your shellcode in the stack or the heap, but you can't basically jump to it because it is being protected, right? So this is called the depth or data execution prevention. So if I take some info about this, so this is called dep on next, right? So commonly called as dep on next. So this is basically enabled in GCC also 4.1, and this can be disabled by saying minus exec exec stack, right? So by doing that, so again, if you can get this terminal, so you can get GCC. So you can say minus exec exec stack, this stack, so that will solve that problem, right? Exec stack, yeah, so that will disable it, right? And there are some other things called packs which is in the kernel level. All right, so these are some other protections, and then finally there's another very important one called ASLR, right? So ASLR is a one that we have all discussed. So it's a very detailed discussion. So basically the ASLR will help you to create, if it tries to help you, the developer, ASLR will create an environment where it will give different memory elements, right? So once you execute in things, you'll not be able to guess, right? So because they do randomization, they'll be not be able to guess the memory something is created. So that's the value of the ASLR. So if I try to create a new page here and just try to give an idea about ASLR. So let me bring this figure. So as you can see here, so if you look at this, so when you create a memory at, so this is a PE file, portable execution in Windows. So it creates this memory, but when you restart it, it creates in a completely different location. And please check like this text area, data area. So you have learned about this, the process data. So all these things are created in separate memory locations. So it's very hard to guess from someone when this or where these locations are created. So this is the value of ASLR, or called as address space layout randomization. So memory protection techniques that tries to prevent an attacker from creating a reliable exploit. So they cannot do that because there's no reliability, because it changes place to place, right? And here also you can see the higher 2 bytes get randomized, but some of them are not randomized, but other things are randomized. But there are different techniques of bypassing ASLR also, which you can discuss, of course. But remember, it's not that easy to do it, right? It's not that easy to do it. All right, so that's cool. So if you talk about ASLR, that also can be bypassed, right? And also it can be disabled kernel wide if you want to. Kernel wide also you can disable it. Okay, so this is basically how you do that. So it's put it here. So you can type this command proc sys-kernel randomize VA space, and you put 0 into it. So that's what I'm doing here through echo. So it disables ASLR temporarily. So now when you're doing these experimentations and you're doing POC, proof of concepts, so these things do really matter. So you guys can try out these options and run your codes and say that, okay, this works when ASLR is not present. So likewise, there are options to try out. All right, so this can be quite interesting. All right, so now we know that how it really works out, right? So now we'll continue. So so when this particular lesson, when you talk about return-oriented programming, we are not trying to address all these things, all these specific cases. Canaries can be simply exploited, but we are specifically talking about this situation of NX. So this is quite a difficult situation to handle, right? So we have seen the format strings, like we can exploit any of these situations, but especially the newer compilers, it's hard to break, especially these things like NX. So because it doesn't allow us to play with the stack. So we have to figure out a different mechanism, because the problem is we cannot inject code into the stack and do that. So then how do you do this? Like, that's sort of the issue. So what the NX does is the executables are not permitted. So we cannot bring in executables from outside. So then we have to have interesting mechanisms how we can run exploit code. So this is what we are trying to understand. So I hope the problem is clear to you, because external shell codes are not permissible to run in our memory or the stack. So that's a bit of a tricky situation. So we'll try to address this situation now. Right. So as we talked about, so our consideration will be more on the NX issue or the dep issue. Mostly they are both referring to the same thing, NX or the dep. Right. So what happens is it doesn't execute code or not data. Right, and data areas marked as so the data, if you have data areas in your stack or even your program memory sections, so they are marked as non-executable. So especially the stack is not executable, and also the heap is also not executable. So these are the places where you run things. So these are not executable, in the sense we cannot run codes from externally, and these are hardware enforced. So this says it's a hardware enforced thing. Hardware enforced, and you can load your shellcode in the stack or the heap, but you can't jump to it, so you cannot execute it. So even though you are going to put something here, you cannot do the overflowing. So that's the problem. Or you can do the overflow, but still you cannot run it. That's the irony here. Right. So all way of doing it is like you are corrupting the memory, right? First leveraging the memory corruption and direct process execution, the injecting the shell code. This is what we have done. So if I try to bring down figure to explain this, so this is basically how you deal with the exploitation in the old way. So you do the memory corruption, then you get the control of the EIP or the RIP, RIP or the EIP, and you can jump to the shell code. So once you, before you get the EIP control, it's called the pre-EIP stage of the attack, and then you talk about the post-EIP. So which is basically you are taking control of the shell code. So this is we have done actually. So you probably can remember this. If not, please go through and the exams are coming. So make sure that you go and look at it, right? And now we'll see how the Stack Overflow works. So, okay, sorry about it. All right, so here, so I'm taking these slides actually from LinkedIn. I'll put it in the description from a person called Shaumil Shah. I will give the link to you. So, and I have to thank him for the slides. And okay, anyway, for here also now what happens, if you can go through this, pre-IP override the return address in the frame. You can remember, right? So you override the return address and then set the EIP to land in the shell code in the stack and then execute the shell code from the stack. So we have done that. So basically exceed the bounds of the local variable. So that's what we have done in the stack case, right? So you always try to get one of those vulnerable functions somewhere here, and then you get control of it, and then you go down in the line or the lane and goes to the local variables and override saved return address in the frame. So if you find the return address somewhere here, you override it. And then shell code is injected, then you are going to get into any other place where there's a shell code, and then you are going to overwrite it. Right, so basically EIP can be set direct to the stack address or perform a jump to the register. So you can do a jump also. There are two things that you can do, of course. The call, that's one thing. The other one is called the jump. So these both things are possible in the old way, right? So but now, of course, later on you'll see that this is not possible. All right, so now we jump into the postmodern world, right, where you have introduced NX and depth. So when you have NX and depth, what's going to happen? Right, now we'll see what's really going in the depth. Okay, so if you carefully look at this, right, so in overwrite and return address you can do, get the EIP that you can do, but now even though you load it, entire stack region is marked as non-executable. So that's bad. And EIP can land in the stack but no execution. That's really sorry. I'm really sorry. So I can't execute. So CPU refuses to fetch and execute. See, that's you are in a dead end. So the exploitation goes haywire. Okay, so really sorry that you cannot exploit it. That's what they are saying. All right. So basically, this is the reality of the story. So EIP movement is restricted. Can't jump to the heap. Can't jump to the stack. So these are the positions where you can't do anything. Can only land in executable regions. Can only land in executable regions. So these areas can be you can go into, but ideally you'll not be able to execute anything in the heap and the stack. So as exploiter, you are in quite a difficulty. So solution. So now what to do? See, cat and the mouse game. I told you earlier. So so we are living in a world. So our hackers, exploiters are a bit ahead of the rest. But fortunately, unfortunately, this was academic paper, research paper who introduced this concept. So you can't say all the bad people identified these things, but the purpose of doing that or the research is to make the world better. So otherwise, if some bad person would have identified this, they would have attacked it and hacked it and exploited it and blah blah blah. So this basically helped in opening up eyes. I think this was introduced in DEF CON. I have the name of the person, the researcher from Stanford. All good things come from those places. Anyway, so what the argument that it brings is we can borrow bits and pieces of the code. So now see the problem here. Problem here, you cannot get external code, right? You can get external code, even though you can write any external code, shell codes. See, there are so much of shell codes there, right? Let me find shell codes. You go to shellstorm, uh, shellstorm. You find plenty of exploit codes, guys. So you can, if you write exploit code, that's fine. If you can't write exploit code, that's plenty for you to deal with, right? So, but the problem is you can't do this, right? You are not supposed to bring down things and run here. It's out of your league. So what you can do now, what you can do, if you carefully look into this problem, the problem is where you can't bring the code, but still there's plenty of code already in the memory of the process, right? So it's a very interesting piece of thinking. So there are a lot of, now say as an example, in your shellcode, there's instruction, say 0x something like this, 0x 50 to 0x 100. So it represents something like a move A to EDI or RDI. So this is what you have to do, like in this particular part of shellcode. And the cool thing is these sort of cool snippets, say the memory snippets or the address, sorry, what do you call this execution snippets are available in the already existing computer's memory or the stack or the heap or the wherever. So only thing you have to do is now to find out what sort of similar stuff is available. So we had to borrow bits and pieces of code from the existing up and running system. So you have to borrow bits and pieces of the code, and that already exists in the executable region of the process. So when you run the stack, when you run the heap, and when you find the data sections and the no data sections or whatsoever, you can find this information. So if you can find a similar instruction, because these instructions are very similar in nature, like so move A to a EDX or EDX to the A. Right? So these things are repeating instructions, reusable instructions. So when you look for this, you can find them. So what a cool concept it is. So basically, these things are called gadgets, right? So gadgetics, these are called gadgets. So these gadgets are available in the computer's memory, right? Or this running processor's memory. So just you need to borrow them, right? So and what you need is you not need in your shellcode you not only have this, but you have many other things, 0x 50, 60, 100, so many other things. So if you look through a shellcode, guys, so you can see all these instructions now. Right, these instructions. So this can be one gadget you can find in the already existing the stack. This can be something that you can find. This can be something that you might wonder how that happened. So this can be a very specific statement. How can that be available? It's available. That's the thing. That's the cool thing. So these things are available. Say maybe there's a situation where there's a printable statement. Maybe that's not there, but you can generalize these codes. So once you generalize your execution, that can be found without much of a problem. So these are called gadgets. But remember, one gadget would not be suffice, right? So one gadget would not do this. You have a shell code to run. You have a set of instructions to run. So in that case, you need what? Chain. We call chain of gadgets. This chain words comes everywhere. Gadget chain. You have to have a chain of gadgets. 1, 2, 3, 4. Likewise, you have to have. You can find chain of gadgets. So you might say 10 sequential gadgets. You find them in a sequence. You run them. Blah. You basically get your shellcode. Again, so what's happening here? So we'll take another page. So now you have a program which you runs in your computer's memory. There's a small vulnerability, right? Or not a small, it's a vulnerability. Because of vulnerability, you can go and fetch the return address, and you can of course attack the return address, and then you can go get a shellcode. Right. Now you have the shellcode, you can bring down to the stack, but you cannot execute it. So this is fine. Up to this point it's fine, but here it's not fine. So now what you're going to do is when you have the return address, you guys can return it with programming, right? So you can return it to a place which is already there in the stack, where you have the needed shellcode built in. So actually you don't get the same exact shellcode anywhere, right? So don't try to be stupid about it. You will never find the shellcode in your computer's memory, but you can break your shellcode into smaller parts, which are called these gadgets, smaller gadgets. So these things can be found in the computer's memory. Don't worry, we'll try to do this exercise and you'll see how this will happen. This will happen automatically, right? So we can find it, right? We have tools also called ROP, right? So if you can remember, see. Yeah, that was the ROP, right? That was ROP. Yeah, so ROP, there's a tool called ROP, which you can get these gadgets. All right. So that's sequence of things, and then basically you execute it one by one after the other, right? So then you can get the same situation, get into the same situation that you normally do in a shellcode execution. So this is what is called as return-oriented programming. Use the returns to get into gadgets, and you program it, and you get something done. So maybe I tweaked the definition a bit. Who cares, right? You don't need the definition. Get the idea, then you are good to go, right? So it's basically what you call as orchestrating a code execution. So you orchestrate the code execution from the different places. So assume a series of cards where each card indicates an operation. The code for that operation is present in the executable region. So and the binary or shared library. Card shall contain the access to the code. Now here there are two major areas that you can discuss. So there's one major area called return to libc. So this is quite interesting thing, return to libc. And then of course the pure version of return oriented program, ROP. So return to libc is also quite similar to ROP, but because it uses returning. So but here the difference, I'll tell you, here the difference is it uses some method called system library. So actually in any C program that you run, they use a library called libc. So libc is also contained in some interesting code segments, like so the famous example that we always use is bin/s, right? So ls, bin/ls. So this is already there in the system library. So you can once you exploit the return space, you can go to the system library. You can go to the system library and execute something. So I'll do this experiment with you guys, and you'll understand this. But here the only thing is in the libc, return to libc, it's having some limitation, because you can't simply create a exact shell code. That's where ROP comes in. Both uses the same concept. Only thing is ROP uses gadgets and chain of gadgets. All right. So now you can create a chain of gadgets and do this. So if we try to give a sort of visualization of this, let me go and get the visualization, guys. Oops. All right. Okay, so this is what happens. It's like card. It's called the gadget. Execute A, take next card. So execute D. So always after each execution of the gadget, you go to the next one. You go to the next one. You go to the next one. So you have gadget chain of gadgets. End of the execution, you will get what is expected from your exploitation. It's what you do basically. So these operations have to be thought about and do it. So please understand, you have to, as a hacker or the exploit developer, you have to look into all these gadgets. There are automated ways that we can use, but still, please understand, it's not very straightforward. Can be quite difficult, right, to do these things right. So you have to learn a bit to do it, right? And of course, the origins of the first idea of ROP came in 1997. The return to libc technique, right? So again, this was used. This was in 1997, right? The return to libc one, not the ROP one. Please understand, it's 1997. Return to libc. It's called RE2, RET2, libc. Libc. Sorry. That's the one which is used earlier. Again, device to defeat the non-executable stack. Right. So again, what you do is return to existing function using the EIP. If you don't have a shell code, we can return to a system function called like bin.sh. right? So how it does, we have talked about, we'll do experiment as well. So if we want to get a very simple example, if you look at a function code, right? So we'll take a function code. You can get a function code like this, right? So these are obvious functions which use string coffee, which is a vulnerable code. So this sort of code can be used to execute a return to libc attack, right? So what you do there would be you can get into the stack frame. So then you can go through the buffer and go into, so let me get the figure and explain it to you. Uh, so you get the stack frame from function one, right? If s points to a string greater than 80 characters, it will result the stack overflow, right? The return address will overwritten by the attacker, right? Control the value. And when function one returns, EIP can be set to an arbitrary address. So this time, what is the arbitrary address, guys? So the return to libc, of course, you have to find the system, where's the system library, and then onwards. So first, of course, you have to find out the system library. System. So system actually, you can do a GDB and find out these functions, right? It's not that hard. So if you do things quickly, it's not that hard to find out. Let me do something. I have GDB. Yes, I do have. Okay, so okay, I'm going to write where am I? All right, so I'm going to create a directory ROP. All right, so I'm going to write simple C dot C. So I'm going to do hash include stdio dot stdio dot h and int main arguments we say int a equals 5 and equals 5 and do a printf. We had to do a printf. Hello world. What we do. Alright, GCC, I don't need much, -o, simple. Alright, run the simple, hello world, that's fine, GDB, hello, okay, that's not okay, what happened? Simple, yeah, so GDB, simple, yep, done. Oh, alright, so I do info functions. Debug main. Oh, sorry. Make one main. Run. Info functions. Oops, sorry, I cannot find it. Oh, that's a failure. What is that? System protection. Alright, so I'm running the macro. So what I'll do, I'll quickly do the same one in my Windows Mesh Tally box. I don't think it will be the same issue. Sorry, I have to repeat it again. Okay, I have a program here. Do I have a program? Yeah, so I have the spy program. So GDB test3 test3.py. Okay, let me. So write a small quick C file. Simple C. So world and return 0. All right, that would do. C simple.c minus o simple. All right. Okay. Then I'm going to run this. Everything is fine, and then I can GDP simple. I can do the object dump. That would do. Object dump minus r hello. So simple. Okay, that would do. All right. So now if you check here, you can see the libc. So libc is everywhere. If you get this stuff, you basically know that libc is everywhere. Right? So this is what I want to show you. It took almost 5 minutes to do that. So libc is everywhere. So you can see from this GOT that is available. So when you find libc, you have the system there, and you can find it later on. I'll show how to do these things later. And then you can go and get into the BNLS, right? So then you can access that, right? So that's what you are doing here, right? So any program would have it. So the next step, of course, is to jump the shellcode the regular way, right? So the regular way you can jump to it. Let me get the stuff here. So jump to the shellcode regular way, traditional way of implementing a post EIP jump to shellcode. Other technique involved, trampoline jump or jump to register. You don't need to do that. Either way, EIP lands the stack memory, so occupied by the shellcode. So this is fine. This up to this part, there's no concerns, right? So now the problem appears. So what's the problem, guys? Up to the things that you have learned. Yep. What's the problem? The problem is jump to shellcode with depth, right? The traditional way does not work if stack is marked as none. EIP cannot be made to land to stack memory. This is not possible. This is traditional way. EIP must stay with the binary or the shared library. So this is the problem, right? So this is the problem. Okay, give me a second. All right, so it goes the traditional way. Yeah, sorry. Sorry about it. Yeah, so if you look at this one, so EIP cannot be made with stack memory. EIP must stay within the library or shared libraries, right? All right, so now we'll see what's the next step. So, so in the return to library C, so this is the format it works out. Go there and try to understand it. So basically, this is how it happens. So now you can't go to the shellcode. So basically, you return to the system, right? So you have to find the address of the system in libc, right? So function 1 is made to return to the system function call by overriding its return address with the address of system function, the libc. So now I showed you like how to get there. So that's not a big deal. So we'll try to find it when you're doing our demonstration. And then you can, of course, look at the address of string in binsh, right? So once your first step is to find out the system, guys, as a system function call. So you find it. There are techniques to find the system. It's not that hard. You can go to GDB and find the system process. It's a P system that will give the address of the system. The second thing is you have to find out where is this particular command that you want to run, which is binsh. So this is, and you have to find the address of that. So a fake calling from frame for system is appended after the return address. Return address of the system and the parameters are also should be given. So these are the parameters bin and sh should be given. So this is the second one, is to find out where is the string bin sh and then to find the address of bin sh. So basically what happens when you execute this code is nothing much. You can get the shell and the prompt, and you can basically find the files in the shell. That's it. So it's not a big deal, but still this model, this POC can be used to do exploits. So this is the return libc. So, but remember here, you don't use much of gadgets because you don't need a gadget. If you want, you can do a gadget and do this as well. But in the pure format of return to libc, doesn't use much or gadgets, right? So step by step, if you look at this, right, so this is what's really is happening. Right, let me get this guy here. All right. So just try to understand a bit, a quick session. Yeah. So what's happening here? So address of the system is in the libc, right? So before function returns, ESP points to the overwritten return the address. So this is libc and system, which now contains the address of system, which is cool, right? So of course, what's really happening is you are directing yourself to libc system, to this place, right? So that's what happens there. Not a big deal, right? So what happens after functional returns, the saved return address is popped off the system stack and EIP returns to the system function. Right, so this is good. So this method, you can do some interesting things, but possible to invoke arbitrary functions simply by placing a fake frame. It is also possible to return to EIP control. So this is like the base, this is not the real return program, but this is like the base of it. So it's cool, right? But there are things that you cannot do from pure return to libc. All right, so now it's a good time to jump into understanding what is basically is this concept of return oriented programming, right? So we have actually learned the basics now, so we'll try to understand what really happens inside. Right, okay. So now we'll try to understand ROP in detail. So we'll try to get a example function. Right, so let me get this. Right, so we'll find this calling a function. So you have the main at 3, 4, and you have a function at right. So yeah, so that's going on. All right. So now think this is your function, and what would be the stack frame? So we'll try to get the stack frame. So stack frame would be that complicated. So this would be the stack frame for add 3, 4. So you find yeah. So this is you call the add from here, and you find the stack frame for add here. So that's basically how it works. So you'll have a return address here, and the arguments are passed as variables. So this is the visualization of the stack. Right. So add is about to return. So add is about to return, and return after epilogue to add. So you have the epilogue here. So what does the ESP points to? Immediately before the RET, right? So if you look at the ESP, so ESP is basically pointing to immediately before the RET. So now if you look at the stack after the before the returning, right? So if you want to visualize the stack before the returning, so this would ideally be the look and feel of the stack. All right, so this will be the look and feel of the stack. So yeah, so this is where the ESP, the stack pointer heading to, right? So now what's going to happen, right? If you assume, right, if there's another function, right? So if there's another function here, just to make things complicated, right? If you look at another function, which I'm going to take it here. So stack of, okay, we are in this. All right, sorry for, yeah, so now, so what's happening here is, if I go through it again, so you have this other function which you can call. So after that, we can call add again if you want to. So what will happen is you're going to call the function, and then of course you can do the overflowing as normal, is in string copy, and before the return ESP will be here, and then the EIP will be pointing here, and the EI base value will be here because now it's all A's. So it will be of value 0x 41, 41, 41, and 41. So that will be the value, right? So what is going to happen before the return to the address or the ADD, you can insert a fake frame and make the function 1 return whatever its value, whatever the value it returns. So let me write it down. So so now we are planning to have the function add here, right? So for the add, you have to put some values. So the function 1 will return the values to this add, right? So it can be of any two values. So it can create fetch a new frame, right? So the purpose of creating this one is to create a chain, as you can see, right? So in this case, these are all pre-built functions that we can use, but later on we see these gadgets can be created out of thin air, right? So by looking at the functions. Right, so once you do that, the stack would look like this, right? Stack would look like this. So this will be the look and feel of the stack, guys. So you can see it's overwritten, and you can now return addresses or return functions as you want. So now you have the right, because you can do that, but what you're returning is all the things that you have already you can have all the control of. So you can have control of all these things, right? Uh, yeah. So once function 1 returns, so this will be the structure of it. And if you look at the running of the program, so that's some of the things. If you don't understand, don't really worry. Once you do the demonstration, this will be crystal clear to you guys. Right, so now the ESP is here, address of add, right? So, and then of course, the next step would be you are returning from the address, and this would be the structure of the array, sorry, the stack. So this is the structure of the stack, sorry about it. Right here and go here. So this will be the timeline, all right? So it will address or the add removes, returns from the addresses for ESP. All right, so now this process shows that you will be able to load any other function, right? So in this case, these two functions are our own functions, but later on you will see that this can change, so we can change this and use our own functions. So that's possible to do. All right, so I'll stop from there. So uh, so next one we can start with the demonstration and all that. Yeah, that thing, yeah, that should be the case. All right, just give me a second. We can look at. No, we'll come back to this the theory section. Otherwise, you'll get bored up with the theory. So I'll come to the theory sections bit after. Yeah, so a bit after, and I'll try to explain the rest, right? Rather than going from a bit of a theory. Yeah, so I'll do a demonstration and come back and teach you the rest. All right, okay. This will be part 1. So we'll meet from part 2, which is the demonstration. All right. Thank you, guys.